Hello everyone, welcome to the JK Academy. This channel aims to talk about architecture and urban design in the most simplest way. So if you're interested, please subscribe to my channel. Today I'm going to lecture about sustainability. And sustainability is really important, especially because of the SDGs. I think you all know the SDGs, and we are very responsible for this because architecture and urban design, it is involving development, and then we need to think about sustainable urban development, and then also in terms of community we need to think about the social aspect. So today I'm going to focus a little bit more on the theoretical part, and then also in terms of the social sustainability, and I would like to give a framework as such seen in this content of today's lecture. Because the topic has a lot of content, I'm going to break the video into pieces. So if you want to see some things directly, you can actually skip some of the lectures and go directly to the video that you would like to see. However, it would be nice to actually see the whole thing, because I will be referencing one the other. So to begin with, I will talk about a very theoretical model of the sustainability. So when you talk about sustainability, actually what does it mean is, in terms of ecosystem, we try to make ourselves balanced. So to look at this, it's more useful to actually reference from not the human beings, but actually from bacteria. So now we move into the world of bacteria. So there is this formula to actually model the population growth, and which is called the logistic equation. So logistic equation is a common model of population growth where the rate of reproduction is proportional to both existing population and number of available resources, all being equal. So looking from this formula, I mean, you don't need to really understand the formula, but you might like to understand what is there in terms of the parameter. So X is about the population, and the curve is actually showing the population growth. The K, which is this, is about carrying capacity, and it's a technical term that means environment maximum load. So environment has a maximum that can cater to a certain population, and this is being expressed through this line here, which is K. So this is the amount of capacity, environmental capacity, that exists in a certain world. R is the growth rate and time is T. So time is this. Okay. So to understand this curve that you are seeing here, it means that in a certain capacity, in a certain environment, there exists a bacteria. The bacteria will start growing in the rate of R, and then it will expand the population until a certain point that is within the carrying capacity, and then therefore it stabilizes there from this onwards. So this logistic formula shows how in the bacterial world the population is being stabilized to a certain point, which is in reflection to the amount of carrying capacity that exists. So you can see from here, and then to understand this, the graph, this zone here, which is the A, is about initial stage of growth. So it starts from small population, it grows in an exponential manner, and then therefore it is unstable. But then it reaches to a point, which is the zone B, and it is a saturation stage, where the growth slows and stops, and then it becomes stabilized. So instead of understanding unsustainable and what is sustainable cities, we try to go back and be a little bit more primitive to understand what is unstable and stable equilibria. So instead of looking at the city in terms of many aspects, we just simply say that city is an environment or a landscape. So it's a simple model to show this. So this is us. And then the city, of course, city has many complex elements inside, but we just simply say it's an environment or it's a landscape. And then instead of us human beings, we try to be a little bit more than a bacteria, but less than us. And then so we will symbolize us representing through the behavior of ant. So this simple model is about the ant moving around in an environment which is a landscape, and we try to understand how this growth, the population growth, will reach to a point of from unstable condition to stable condition, and as a whole we try to understand what is sustainability. So I will introduce a simple model which is called the sugarscape model. So now you see the ant and the landscape or the environment. The landscape has it is a mountain of sugar. So you see this green part here, which is actually the mountain of sugar. You need to use your imagination that this is actually a mountain of sugar. And of course you all know that ants, they love sweet things. So in the mountain of sugar there will be a lot of ants trying to get the sugar or trying to get their food. So the mountain of sugar has certain gradients, so the darker it gets, the more mountain of sugar that there are. Okay. So this is a simple explanation of what is the landscape and what does the ant do. So the ants, they crawl around, they walk around the landscape, and then they would try to grasp the sugar, and then they will eat. So the simple rule here is that the ant, they'll find a sugar and eat and then metabolize. And then it dies when they are out of stock and there are no more sugar around the landscape. And the simple rule for the mountain of sugar, which is a landscape, the amount of sugar decreases as ants eat the food, and then it recovers when it is left for a while. So this part is actually represented through here, where you can see the red, they are the ants, and then the different green that you see, they are the different amount of sugar that exists. The darker it is, the more sugar exists in that spot. So the ant will walk around the mountain of sugar, and then it will stay, and then they will eat. The ant will eat the sugar, and then they will metabolize, and then they will move again. So it's just a simple simulation, repeating this eating and walking and eating and walking. And then meanwhile, for the landscape, once the ants eat the sugar, it will turn black. So the black parts, there's nothing there. It's an area that is not so fertile, so therefore there are no sugar around the black area. And so when the ants, they eat the sugar in a certain spot, you see these black parts where the previous ant has eaten the entire sugar, and then therefore it's empty now. And then meanwhile the time moves on, these things will regenerate. So we will see a simulation. So now I'm going to show you the simulation. You see that the landscape is here, and then the ants has been placed randomly into the landscape, and then they will start walking with that simple rule. And then here there is a graph with the population and also the time. And then there will be the graph of the population that will be showing as the simulation moves on. And so I start from a huge number of ants that has been placed randomly, and then you will see how it stabilizes in balance to the carrying capacity, which is the amount of the sugar that exists in this landscape. So you see how, so from this you can see how it starts from a big number of population, but it stabilizes at the at the rate of 100 in terms of this simulation is 100, and then it stabilizes at this point. Now I'm going to show you another model, which is applied model of the previous simple model. So this simulation has a season, and the season is expressed through this line here, where you have something like the equator. You can imagine it's like an equator where you have the northern hemisphere and then you have the southern hemisphere. When the northern part is a winter, then the recovery rate, the regeneration of the sugar, the mountain of sugar, is slower than the ones that are in the southern hemisphere. And then the season switches, and then you will have the northern part, which is like summer, and then you have the southern part now being winter. And of course in winter time, again you can see from the diagram here that the regeneration process is slower, so you see more of a black part, the black, which means there's no more sugar there. So I'm going to show you this simulation, and you will see how the population will change. So in the simulation, you can see how when the season switches from winter to summer, the ants who are in the fertile area, they try to move because they are facing the winter time, and then they try to move to the other side. But then if you are a bit far away from the landscape, those ants, they are not able to reach, and then therefore when you see the population over time, then you see this a population decrease that happens here. So what you can understand from this simulation is that there is a repetition of population growth that happens when the ant tries to move to the other side, and then there is a stable condition during the summer period, or like in one of the seasons. And then when the moment that the season changes, you will have this decrease of population, because one ends, they will try to move to the other side, but then the ones that are in the edge, they are not able to reach to the other side, and then therefore meanwhile they would actually die, and then the population will decrease because of that. So when you look at the graph, you understand it's a repetition of this unstable and stable condition. It's a repetition of this. But if you look at it in a macro level, so when you look at it in a micro level, then you have this unstable condition and then a stable condition, and then it repeats like that. However, when you look at it in a macro level, then you understand there is a certain sustainability there, because there is a pattern that evolves. So in this society, it is quite natural to have this population decline when the season switches. So this is what is being said. When you look at just this part, you might think it's unsustainable because it's unstable condition, but you need to look at it a little bit in a macro level, and then there you will find a different view. So now I'm going to show another applied model, which is the battle. And now you don't have just the one type of ant, but you will have two types of ant, the red one and the blue one. So in terms of the rule, the simple rule, it's the same. So the red and the blue ants, they will find sugar, it eats and then metabolize. It dies when they are out of stock, and then when there are no more sugar around. However, you add the rules of the battle itself, and the battle between the red and blue has a rule that is the strength of an ant is in relative to the amount of sugar, which is signifying the wealth of that specific ant that has. So the stronger ones, which means the ones who has more sugar, can snatch the sugar from the other colored ants. And then the ant dies when they lose the battle. So this is the simple rule that has been added to to have some relationship between the different agents. The agent means the aunt. So what you can see from the simulation is currently the blue one has been overtaken by the red one. So now the red ones, they are the majority in the society. However, if you see closely, there is this small little like one or two ants, the blue ones that remains. The ones that remains, it means that they are quite strong ones, meaning genetically quite strong ones. And then therefore, it overtakes the other one because in terms of the population, when you have the majority, it means that one ant, they are quite weak. So then it's being defeated by the stronger ones. And then this pattern repeats. So you have one moment that they are more the red ones. But then you will have a moment, which you will see now, the blue one now overtakes the red ones. So eventually, this simulation shows that the blue one wins at the end. So again, if you look into the graph, the pattern of the graph, when you look at it in a micro level, then you see it's a repetition of A and B, which is unstable situation, condition, and then a stabilized condition. So it's a repetition of this, like this. However, there are two types of sustainable condition in this simulation, which is this one here, whereby you have this pattern of stable and unstable condition. However, it moves on quite a while in that situation. So it's also, in a way, it's also a sustainable condition. You can call it like this. However, there is a kind of paradigm shift here, where the blue one, they are defeating the rest, and then therefore the blue one is the one that stabilizes until the end from this onwards. So in a way, okay, this is the sustainable condition, of course, but it's a different sustainable condition to this. You cannot deny that this is unsustainable, because somehow it is a pattern that has been created, and then it lasts long in that pattern. So it's also some kind of a sustainable condition, but also here is another type of a sustainable condition. So you need to be flexible in order to understand which viewpoint you are looking at. And then if you look at it in a micro level, I mean repeating this again and again, but if you look at it in a micro level, maybe it might look like it's unstabilized. However, if you look at it in a macro level, you might change your point of view, that it could be said that it is a sustainable condition. And I would just like to add a small comment on this. So when you do a village survey, so looking into the vernacular architecture and going in the rural area, you will see a condition where it's the lifestyle, it might be very primitive, but from the way that the village has been articulated, there is a lot of thinking behind it. And then when you see that condition, you understand it's very similar to what the simulation has been showing. You really understand that the ones that we are able to see today, the primitive, the vernacular that we can see today, is actually a condition of this state, whereby through a certain battles that they have had with the ups and downs, a lot of them probably they died because of that. And then what you see of today is this stabilized condition. And then the ones that we can see is Okay, the ones that we can see of today is in this stabilized condition, but we should not forget that I think that there were this kind of repetition of the repetition of the stable and unstable condition that they have been repeating until a point that they have reached to a real stabilized saturated condition, which is what we can see, which is, I think, is the second phase of the sustainable condition. Now this simple diagram is actually showing the Earth's surface temperature, the evolution of the Earth's surface temperature, and you can see there's a lot of ups and downs, and then it is going back to as far as 100,000 years ago, and so you understand there has been a lot of events that happened. You have also the ice age and all that in between, and then from here you understand that the last 12,000 years, which is basically here, is unusually very stabilized. So with all these different ups and downs, unstable and stabilized condition that has been going on, you understand the current situation that we are facing, which is in fact started maybe around the period of the agricultural revolution that happened maybe around 10,000 years ago. So how come this agricultural revolution happened, which is actually a phenomena that before that people were actually moving around. They were nomads. But then after the agricultural revolution, what happened is that people started to settle and then form a village. So this is why agricultural revolution is a big event for us. It's a revolution that happened to us from shifting from a nomadic lifestyle to the settlement. And this around 10,000 years ago it happens, and then maybe it was possible to do it because of this stabilized temperature condition that they were facing. So I think the stability of the temperature enabled this agricultural revolution to happen, and then what we are facing now is a state of a stabilized condition. But however, this doesn't mean that we should not we should ignore the fact that the climate is changing. I think we should understand that there is a micro level of climate change, and then there's a macro level of climate change, and then we can feel the micro level of climate change. But the objective is actually to know that we should try to maintain this stabilized condition, and then we should the objective of human beings in terms of development is to maintain this state. And then therefore we need to understand why there is an alarm to this, is because it's exactly the point of the balance between the population and the carrying capacity. So what we have today is the condition where the carrying capacity, of course this is constant, we cannot change this. However, the population growth is changing over time, it is growing, and then therefore the problem that we are facing is because of this state where the population that is based on our activity are beyond the carrying capacity. So this is the kind of alarm that we should be aware of, and what we need to understand is that somehow our behavior and our activities, they are really influencing this carrying capacity. So looking into how to understand the balance between our behavior and then the carrying capacity, so is there a way to measure this impact? So this will be in the next lecture.